Welcome everyone to the third lecture of our machine learning class. Today I'm going to introduce you to linear and logistic regression. So what do you use linear regression for? One of the examples I wanted to share with you is this. So think of the most recent elections you can remember. In some of the states, it was really a close race between two candidates, and the like a portion of the votes were counted in the beginning, and those were those who came from people that actually went to the voting booths. And after they had been counted, the one candidate was ahead of the second candidate with quite a substantial lead. And now they started counting all the mail-in ballots. So those were predominantly sent by people that preferred the second candidate. And as those ballots were counted, the lead of the first candidate over the second one was diminishing. And to be able to predict how this is going to end after all the ballots have been counted, you can do a linear regression and then see what this prediction could look like. So, right, so as those new data is coming in, we could compute our linear regression and then look at when this line actually hits the 100% point. And then this difference here, so this y value would then be our estimate of how much the other candidates, the second candidate, would have gained over the first candidate. Yeah? And this has been done by a statistics professor at Harvard. I recommend visiting his Twitter feed. You'll find a couple of other interesting statistics plots and data. So another example is this. Think of a research question. So for example, how much of a certain behavioral effect can be linked to a certain drug that we want to administer. So we'll run multiple trials with our, I don't know, human patients or mice models or whatever. And then each of these dots here would correspond to a certain outcome, yeah, to a certain amount of drug that we delivered and a certain effect that we have quantified. And linear regression can be used to see if there is some relationship between these variables and how strong this correlation is. Yeah, how much of the variance can be explained by this linear model. And linear regression is a well-known method in statistics. We'll not look into that too much. Here in this lecture, we want to focus on how can we obtain the parameters of this model given the data that we have. So formally, we are given a set X again, which is the set of all data points xi, so x1 through xn. And again, they live in m-dimensional vector space. We have respective targets in the set of scalar values y1 through yn. They don't, in general, need to be one-dimensional. Could be from any vector space, but here we'll limit ourselves to just one dimension. The objective in linear regression is to find a linear function which will have the form of this, so W transpose X plus B. W is a vector from the same vector space as X, obviously, and B is a scalar value, like an offset that we add to each of these dot products. And now this linear function, this linear model, should approximate the labels as best as it can over all of these samples. And since we do have target labels, this is a supervised learning problem. So let's review line equations real quick. In the one-dimensional case, we have a dimension x and the output dimension y, both being scalar values, so one-dimensional. A line really is defined by one central property, which is if you have a point on the line and you look at how much you drop, to a given other point when you go a certain step to the right or to the left. Yeah. So if you increase x a little bit, then you drop or you go up, depending on what the line is, to the other point. And if you go k times as many steps to the right or in the x direction, you will go k times as much down to stay on the line. Yeah, so the ratio, the proportion of this drop in y, or this change in y, and the change in x is constant over all this places on the line. Yeah? So you would usually see an equation that looks like that: y equals mx plus n. M here is the slope of the line. In this example, it's negative, so that's why we have a drop. If it would be positive, then we would have a step up. And n is the intercept with the y-axis. So think of x being 0, so we are here. Then n gives you the coordinate on y, where the line and the axis intersect. So in higher dimensional space, that's pretty much the same. To describe a plane, we use again a product of slopes, let's say. Each of these individual components are telling us how much the respective components within x, so x1, x2, or x3 change. And then we have a constant offset. So, but W isn't just the vector of slopes; it's also a vector in the space, and it's a nice idea that we want to visualize here. So x here is this vector, and this is W. So W is a vector perpendicular to this plane that we want to describe functionally. And now, what's the property that we really want to define here? So W transpose X is the dot product to every X on this plane. And let's disregard for now what B is. This needs to be the same for all the X on the plane. And what is W transpose X? Well, it's a dot product, but you can visually interpret this as the projection of this vector x onto the direction of W. So if W has length 1, the scalar value produced by the dot product corresponds to the length of this projection. Yeah. And now you can see you have a vector W that points in a certain direction, and then all the other vectors that, when projected, give you the same number. They have to stay on this plane. So B, again, is a bias term, an offset that lifts up or down the plane in the direction of W. So in linear regression, our task is not to just describe this plane in the space, but also to kind of represent the data Y that we are given. And also the data points. So the input and the output, may be noisy. So we need this to be an approximation and the best that we can find. So the idea in linear regression is that we minimize the deviations of our predictions to the respective labels that we have. And we average all these predictions into a single number. And this number is supposed to be minimal. Yeah. So formally, we define this deviation as scalar value that's the result of a vector norm, and the vectors that are compared are the vector of all labels and all predictions y hat. And then you can ask, okay, what kind of norm are we supposed to do to use? Well, any norm should be working, but really the most used and the most popular norm obviously is the L2 norm, which is just square distances, and then in the end we take the square root of these summed up distances. So just to visualize maybe what kind of distances here in red in a suboptimal line fit would produce compared to an optimal line fit. Yeah, so you see that if the line isn't really following those data points, then the deviations will be quite large. And if we tune the line or the parameters of the line such that they better represent the data, then of course also the deviations are more. Yeah. Okay, so as I said, we will use the L2 norm, and our objective is our loss objective here. Yeah, so this is the word that we will use in the following. The loss is a function that is depending on the data that we have given and also the parameters of the model. And is given by, as we just said previously, the differences of the labels and the model's predictions squared, and then we sum up over all data samples and divide it by the number of samples. And the learning problem is also called least square. So we are looking for a least square solution because we want to minimize those error squares. Yeah. We use the square function for convenience reason, really. We will see that later on. And also we use this because it has a nice statistical interpretation. And I recommend you visiting this YouTube video here, produced by Frank Noé, a colleague in the math department who beautifully describes that the likelihood of the data and the model is connected to the least square solution. Yeah, so the probability of the data given the model is maximized when the error squares are minimized. Go watch this video. So let's solve linear regression and let's solve the minimization problem. So let's start here. We have our line or a plane equation that should be satisfied for all pairs xi and yi. Yeah, so we want to find the parameters w and b that explain the data. So first step is to put all of these individual equations into one matrix times vector equation. So we want that with one multiplication and add operation, all the data is explained. So how do we do this? Well, it's simple. We create a matrix X, and X is a tall matrix. So the more data that we have, the taller it gets. Each of these rows is one of our input vectors xi, and multiplying this matrix by the vector W results, so the multiplication is really a dot product of each line or each row of the matrix with W. So this is what we want to do here anyway. And then we create two new vectors. We call this vector bold B. So this is a concatenated vector of all the copies of the one scalar bias that we have, and then the result is supposed to be Y. So all the individual yi's are concatenated here. Yeah. But this isn't convenient enough. We want this to be a little simpler, and one of the conventions that you will see is that the matrix X is augmented or extended by a column vector that is only ones, and the parameters that we look for in the W now here become W hat, because we have added the bias value at the end of this. So the multiplication of this matrix times this vector is really the same as in the previous slide. Sometimes you will see the one being added here in the first column of the vector, of the matrix X, and the bias term being the first of this vector W hat, but it doesn't really matter because the sum in the end doesn't care about the position of the bias. Okay, so let's now solve for the parameters W and B. Now we will just look at W, and you can think of this as the W hat in the previous slide. So we want to solve for the parameters that minimize this expression, and we want not the minimum itself, we want the argument, so the parameters themselves that minimize this. Yeah? And again, we look at the norm of this vector squared for convenience reasons, and as you may remember from school, you can minimize this by setting the derivative to 0, and that's what we'll do. Okay, so 0, and please don't run away when seeing this block of equations. It's really simple, and I'll lead you through. So 0 should be so this is the nabla operator, so this is the derivative with respect to W of this expression that we had here at the top. And so this is the square of the 2 norm, and remember the 2 norm is the sum of the squares and then the square root. So that if you then apply another square, the square root will vanish, and then we'll have just the individual sum of squares, and this could be written as the dot product of these two vectors, or of this vector with itself. Yeah, so the vector y minus xw. So these are the differences of the predictions xw and the labels. Now we have an expression of the derivative of a product of two things that are multiplied by each other. So we have to apply the product rule, which is the derivative of the first term times the second term plus the first term times the derivative of the second term. Believe me, I looked it up. That's the rule. Yeah. If you don't believe the rule, then we'll have to go through this in the assignment session. But what is the derivative of this guy? Well, basically, y isn't depending on w, only x w is. So the derivative is minus x, and the transpose will get on here as well. And this isn't we don't want to find the derivation of this, and we just keep it. And then we do the same for the right part here, and this looks very similar. Yeah. Now, if we multiply this into the parenthesis, we'll get minus x transpose y plus, so the two minuses become plus x transpose xw, and then we'll do the rest for the right part as well. It's pretty similar, and then we can condense this into this shorter term, minus 2x transpose y plus 2x transpose xw. Now let's just cancel away those two 2's and get this over to the other side. Then that's the equation that is the solution where this expression is minimal. Yeah? So because it's quadratic, we don't have a maximum, we have a minimum. So this holds true if this expression is minimized. Now we can get x transpose x to the other side by computing the inverse, and then we have a functional expression for our w that minimizes our problem here. Yeah. So this may not work in practice because the matrix x transpose x may not have full rank. So Lewis has written down a short example. So consider these three x's and the corresponding data matrix capital X. Now x transpose x will be this constant matrix, and obviously it has rank 1, so we are having a hard time inverting it. There are two common solutions, and we'll look at them in the next couple of slides. One is ridge regression, and one is the famous pseudo-inverse. So in ridge regression, we do a little trick. We add lambda times I, so these are small lambdas on the diagonal, to the matrix x transpose x, and then we can invert it. And this basically goes back to the optimization objective that we had before. So the distance of the predicted and the given labels need to be minimized, but we also now want to minimize the length of the vector, or the squared length of the vector. And this lambda gives us a little bit of a weight for this objective, but given a certain value for this lambda, this has an effect on the solution. So for ill-posed matrices here, so for hardly invertible ones, there may be many solutions, but now we restrict the one that we get for the argmin to be the smallest vector w. And another thing that I wanted to mention, because it kind of leads over to the next slide, if we take lambda and make it smaller and smaller and smaller and smaller until we reach the limit of lambda equals 0, this matrix is in the limit A plus. And what is A plus? Well, A plus is the Moore-Penrose pseudo-inverse, or short pseudo-inverse, which is a pretty cool matrix. So any matrix A, it doesn't have to be square or whatever, could be any size, has a pseudo-inverse A plus, such that if you multiply it with the original matrix, you get the identity, and that holds for both sizes. Yeah. And so there are a couple of ways to compute this, and I think the most common one is using singular value decomposition. We're not explaining how SVD works. I think there are a couple of very nice videos that show you at least what the intuition of SVD is. But so the singular value decomposition decomposes any matrix into a product of three matrices. And we do this for our matrix A, and then do something with the sigma matrix here in the middle. And by doing that and reapplying this multiplication, we get A plus. And that's pretty simple because the sigma matrix is just a diagonal matrix. So it's 0 left and right of the diagonal. And these lambda values here are just inverted. Yeah. So if they're non-zero, it's just one over the lambda value. So the cool thing about the pseudo-inverse is that it solves our minimization problem. Yeah. X plus times y gives us the optimal least square solution, so the vector w that minimizes this expression. And this can be seen by looking at this start. If this is true, then we could just see what we get if we multiply x transpose x to both sides, to the left and the right. So w becomes x transpose x w, and the right side becomes x transpose x, x plus times y. And as we've seen in the previous slide, this has been defined as the identity matrix. So this collapses to x transpose y. And x transpose xw equals x transpose y was what we found should hold in the least square solution, right? So at the solution of the minimization problem. So two remarks. One is if x transpose x is invertible, then x transpose x inverse times x is the same as x plus. Yeah? And also the solution that we obtain through applying the pseudo-inverse is really the minimum norm solution. So the vector w is the shortest vector that still minimizes the problem, which is a nice property. Let's have a look at a couple of examples. Thanks, Luis, for making these for me here. And you could look at this code and copy paste it into your notebook to see if that really does what it should. But let's think of the following example problem. So we are given a couple of y values, y1 through y5, and corresponding x's that we will hold in our matrix capital X, and do not forget our bias ones here. And the first step is to compute the singular value decomposition of this matrix X, which I hope you will believe me will look like this. And look at this sigma or S matrix. It's as I said, a triangular matrix, and you can just use these diagonal values here and invert them here by computing 1 over those values themselves. And then we put this all together in our matrix X plus, and then we can multiply this with the values that we have given. And then we have our matrix, our vector W, and then we can plot this here to see if it really is a good line fit, and I'm happy that it works. I hope you are too. So this is really a good solution. And by the way, you don't have to re-implement this. It has been implemented maybe 2.5 million times already. Look for a function in your favorite linear algebra library called pin for pseudo-inverse. So this was linear regression. Regression means the outputs are in a continuous space, but you can use linear models as well for classification outputs. Yeah? So if we have different categories you want to predict, then you can use linear models as well, and that's called logistic regression. Let's have a look. So in logistic regression, we again are given our data set X with our n samples from m-dimensional vector space, but now we do have our labels given as binary values. So they're either 0 or 1. Yeah. So we call this a binary classification problem. We have two classes between which our model should discriminate. And in the following, we will model this as a function that maps m-dimensional vectors to a continuum of outputs between 0 and 1. Yeah? So this could be interpreted as the probability of the input belonging to class 1. Yeah? So that's why it's called regression. We do not have distinct outputs anymore. Although we do a classification task here, we model this as a one-dimensional continuous output that is the probability of the sample to belong to one of the two classes. So one way to represent this probability is with the Heaviside step function. Yeah. So in our let's say one-dimensional input space for X, we have samples that all belong to class 0. So this should be output 0 of the Heaviside function, and then we have this sharp step, and all inputs, all x's above a certain threshold result in an output of 1. And usually we have a way of controlling this location of the jump of the step with this parameter tau. So any x will be compared to tau, and larger x's will then be resulting in ones and zeros otherwise. The problems with the Heaviside step function, although it's a nice function and simple, it's not differentiable, and we need it to be differentiable because we want to optimize it in an iterative way, and where we use the gradient. Yeah? And there's actually no gradient defined here at this point, and the gradient here doesn't really give us information of what the better location for this parameter would be. And also it's not smooth. So why do we want to have a smooth output probability? Well, think of the real world data. Obviously has a lot of noise in it, and sometimes classes overlap. And so it would be nice to have a model that kind of also gives you a measure of how confident it may be for a certain input X. So look at this example. We have two distributions, one, the blue one, for the output class 1, and the green distribution correspond to the green data here for output class 0. And as you can see, those overlap already. And so we could model these as Gaussian distributions in X. And then, to obtain an estimate of what the probability of the respective input was, that it is belonging to output class 1, we could just see, okay, take the probability of it, of this Gaussian PDF, and then divide it by the sum of both possibilities, right? So it could be either this or this. And so if we look at exactly this expression, so probability as measured by the Gaussian divided by the sum of both, then we get this nice so-called logistic function. So in the one-dimensional case, our logistic function looks like this. So it maps any real valued input to the interval 0 to 1. So that is our requirement. So that's good. And the shape is, or the form is 1 over 1 plus e to the minus beta x. And beta is a parameter here that controls how steep this this gradual step here is. So large betas make the function look like the Heaviside step function again, and you know, smaller values for beta make this transition smoother. In the multivariate case, we have a mapping from n-dimensional vector space to 0 to 1, and we use parameters that you should already know. So B is a scalar real-valued bias term, and we have W, a vector from the same space as X. And the sigmoid function here takes this form, so it looks pretty similar to this, but it's showing this linear model that we have already introduced before. So W transpose Xi is a dot product between two vectors plus B is a bias, and if you imagine, so this arrow here is our W, and now every other vector that is similar in, similarly pointing to directions that W points at, the dot product will be positive. So let's disregard what B is for a minute. So e to the minus something positive, and let's say it's a big dot product, right? Because they are perfectly in line, or X is really far, in this direction, then this expression is 1 over 1 plus e to the minus something very negative. So e to the minus something very big. So this will be 0 here. So this approaches 1. Yeah, and this is what you see. So the plateau here is for all the different vectors that point into directions with a positive dot product. And the opposite then is true for vectors pointing away from W. So this will be a large negative value. So with the minus sign here, this will be a large positive value. So e to the something very positive is something large, and then 1 over something very large is 0. Yeah? And now the vectors that are perpendicular, they produce a 0. Yeah, and so they should be on the decision boundary. Yeah, so they should be close to 1/2. So with the logistic function, we can now come up with an expression of the data either belonging to class 1 or 0. So it's either the sigmoid or 1 minus the sigmoid. Yeah. And of course, we can write it like this kind of decision, asking for what the label of y was. But usually we conveniently rewrite this as y hat to the y times 1 minus y hat to the 1 minus y. Remember, y is either 0 or 1. So if it's 0, we disregard our y hat and take 1 minus y hat. And if it's 1, we disregard the opposite case. Yeah. So what we now want to do is to find the correct and optimal W and B. Yeah? So the parameters of the model that optimize a certain condition or certain objective, and here we will use the likelihood. So we usually take so-called maximum likelihood estimator, which is an expression that gives you the probability of the data given the specific model parameters. Yeah? So the likelihood, we'll use the equation from the last slide, of x and y, so the data given the model parameters, needs to be maximized with respect to W and B. So we want to get the arguments, so that actual W and B's. And for convenience reasons, we most often use the log likelihood. So, and since that doesn't change the arguments that maximize this previous expression, we are fine. Yeah. The log likelihood now is just the log of what we've seen in the previous slide. So log of y hat I to the yi times 1 minus y hat I to the I minus yi. And so applying the log power law, this log of this brings the yi down, and then you have this expression. And since we want to usually minimize a loss function, we just put a minus sign here, and then this should correspond to the maximization of the likelihood. Yeah, and this expression is called cross entropy loss, and you will learn how to use it and learn also to implement it, not just for the logistic regression task, but also later in other nonlinear models that do binary classification. Let's go through a quick example of cross entropy loss. So let's see, we have 4 different samples here, outputs of our model y hat, and the corresponding real labels. And so you could review this, and I'm not going to do this step by step in the video, but you can just stop and see if we did it correctly. But so given an output label 0 and a model that is close, the loss here is a smaller number, as we hoped, as in the other case where the output is really far away from 0. And also here in the two other cases, this model is a much better model because it's, or the output here is a much better output because it's closer to 1 than here, and also those loss terms, those loss values reflect this. So how do we now actually find, using the maximum likelihood estimator and the cross entropy loss, how do we find the minimum loss weight vector and bias term? So in linear regression, we just did this, and then we had our solution. In logistic regression, we have to do it iteratively, which is very close to what we do in other complex models like neural networks, for example. So the function that I've just shown you, the cross entropy loss, is a convex function, and we don't have to explain what that means, but we are guaranteed to find the global minimum using gradient descent. So starting at a certain point in the loss landscape, we could just look at the direction, whether to walk in this direction or that direction in our x dimension, that decreases our loss. And so we would step by step walk down this slope until we end up in this minimum. And since it's a convex function, we are guaranteed that this is the global minimum. So we start at an initial guess. Doesn't really matter where we are. And then we look at the gradient of our function f, or whatever function we want to minimize. And the gradient of this function gives us the direction in which it's going upwards. Yeah? So we usually go, for minimization purposes, in the other direction, which is the direction of the steepest descent. Yeah? So that's why it's called gradient descent. We use the gradient to descend this landscape here, and we use a parameter here, nu, or other lambdas I've seen, or gammas, as a learning rate. So this is really the step size. Yeah, for each of these steps that we do, and the superscript here gives you an iteration index. So the next position and x is here really the input space, but could be any other parameter that we want to optimize for. And then at some point we converge, and then or our steps are too small, and then we should stop doing this, and then our estimate is the optimum. So for the cross entropy loss, the function f is our L here, our loss function. The x's and the y's are given, and we want to now get the gradient of this loss function with respect to the weights and the biases. Yeah? So how does the loss change? Yeah? So dl if I change the weight, or how does the loss change if I change the bias? And those entities, those terms, are given by these expressions. I'll show you a link in the description of the video that points you to a derivation of this. For now, you can just believe us. So this gives you for a given x and the current parameters w and b and the labels, an expression of how to change. Yeah, and we go minus this direction in our parameters. And it's also something that's kind of meaningful in the way that we have our labels, and then we have a comparison with our prediction, and that kind of gives us the sign in which direction we walk. Yeah. So usually we don't do this point by point or sample by sample. We usually take a batch of samples. So let's say 32 or so samples, and then we average our gradient over these input-output pairs and the gradients that we receive by evaluating these terms here. And then our update is then done after processing or after calculating the gradients for each of these 32 samples. Yeah? So to summarize, today we've looked at linear regression, where we have continuous labels in a very simple model with parameters w and b, and we've optimized the mean squared error with the pseudo inverse, which is like this and not iteratively like we've seen in the logistic case. Here we have binary labels and use the logistic function that still uses this linear model here, and a different kind of loss that we call cross entropy. Yeah? And this is minimized by gradient descent, which will come back many times in the next lectures. And now you may want to ask, so what about multi-class classification? So what if we had 10 or 1,000 different output classes? Then we do have a so-called softmax classifier. And I will not show you this in this video because it's already too long. But if you hold on and stand by and visit those lectures, we will see the softmax function and also the categorical cross entropy loss that we can use. It's not bound to be used only with linear models. It could be used with any model. So with that, I want to conclude this lecture. I hope you enjoyed it. Please find the mistakes in my slides. Get back to us with your questions on next Monday. See you all soon. Bye.